Alright, here we go. Chemical kinetics from a conceptual point of view. Um, yeah, found this, look really cool. I don't know why. Love these standards, yay. Alright, so quick review of the collision model. We talked about it last time, having to do with a golf club hitting a golf ball. And obviously you have to have a collision with enough energy to produce a reaction, or hit the golf ball straight. We know that the amount of energy is the activation energy. Along with the collision, you must have a proper orientation. So hitting the golf ball with a golf club other than the sweet spot is not going to give you the desired outcome. Reactants have to have proper orientation to allow the formation of new bonds and the actual conversion of reactants into products. Again, activation energy has to do with, getting to the top of that hill of the graph. Minimum amount of energy. So here are spark plugs in a car. As the pistons fill up with, not pistons, whatever they're called in a combustion engine, fill up with gasoline and oxygen, the spark plug ignites and makes a little explosion in your engine, hence why it's a combustion engine, and it forces the piston down. We talked about exothermic process. Products are of lower energy. Endothermic process. Products are of higher energy. Here's our graph again, showing how the blue and the green are opposites. NO2 is decreasing, NO is increasing, but at the same rate because the stoichiometric coefficients are equal. And oxygen is half that of NO because it's 1:2 ratio. So we can measure disappearance, we can measure appearance, and they are proportional stoichiometrically. So again, you've seen this before, just kind of quick recap. Reaction mechanism, not part of your class right now, but just talking about how all reactions usually go through a series of steps, not just a single step. So the overall equation doesn't really tell us how they become from reactants to products, but it's basically just an overview of a summary of the whole process. We know this by the arrow, represents reactions to products, but there's no indication of the mechanism. You just see a reaction, you don't know the actual in-depth involvement of everything going on. If you were to look at a mechanism and see the multiple steps, they're usually described as a slow step or a fast step. The slowest step determines the rate of the equilibrium, or the rate of the reaction for that matter. No reaction can be faster than its slowest step. Kind of like the buffalo, when they go to the Serengeti, they travel in herds, and the whole pack must go as one, and as the lions and the tigers and the bears, oh my, kill off the slower buffalo, the overall herd does get faster. So kind of like reactions, the reaction can go no faster than the slowest step. Are factors that affect rate, temperature effects. Obviously, increased temperature is always going to increase the rate. Things react more, things move around more, have a higher ability to collide, and also gives more energy to the system. It is easier for all reacting particles to get over the hill. Surface area, obviously more surface area, more opportunity for collisions. More opportunity of collisions lead to more chances of having the proper collision. So a spoonful of sugar versus a sugar cube. Those of you that drink coffee who put sugar in their coffee sometimes use, a spoonful or cubes. The spoonful a granulated sugar will dissolve much quicker than the sugar cube, because everything inside the sugar cube will not be affected by the hot coffee until the outer sugar crystals are dissolved. Concentration usually increases rate. Again, depends on the order of the reaction, but obviously increased concentration, more things have the ability to collide. Again, everything goes back to the collision model. And then catalysts, we know what catalysts do. So a couple things. Catalysts, we know it speeds up a reaction by lowering the pathway. Enzymes, now chemical catalysts and biological enzymes, they both do the same thing, but they are completely different. Homogeneous catalysts present in the same phase. So if everything's aqueous, the homogeneous catalyst is going to be aqueous as well. And a heterogeneous catalyst means it's in a different phase from the prefix. So if everything in the reaction is going to be liquids or aqueous, then the catalyst is going to be a solid. One example is platinum. Platinum plates can be used as a catalyst, a heterogeneous catalyst. We're not going to get into the actual mechanism of that, but realize that they're helping out in multiple ways. So looking at the graph, you can see the black line represents without a catalyst, and the red dotted line, dashed line, represents with a catalyst. So we can see that the reactants stay the same, the products stay the same, but the amount of energy required to start the reaction, much lower. So more molecules have the ability to get over there. You'll make more products quicker. Here from an exothermic perspective, same exact thing. Reactants stay the same, products stay the same. However, the pathway to get there, shorter. Mount Everest versus Mount Diablo. Which one's easier? That's rhetorical. Yosh. All right, that is it for a little quick review on kinetics. Thank you.